So, hi Tife.
Hi.
Hope you're having fun wherever you may be. In the month of January, we're going to be doing integral techniques. So in particular, today and tomorrow, we're going to look at improper integrals. Then we're going to look at integration by parts. And we're going to have a whole smorgasbord of different ways to tackle integrals. We're going to take a look at trig forms. When we combine those with trigonometric substitution, that's going to give us a large arsenal to work with. And we're going to take a look also at partial fraction decomposition, which is really an algebraic technique that we can use for certain intervals. This will actually keep us busy and off the streets for the month of January. See, what else do we need to do? That's kind of it. And that's going to clear the way for us in, and then we need to do applications of integrals.
Okay.
That's going to be our last week in January and probably the first week in February. So that's going to include all of the areas, volumes, arc length, etc. And that's going to take us into February. And then February proper, we're going to start on a huge idea and analysis that is totally new for you guys, and that is going to be the idea of representing a function, an arbitrary function, in terms of a polynomial, or ultimately an infinite series. And that's going to be the bulk of our work in February, maybe early March. And then after that, we're going to take a look at polar coordinates and some vector analysis, and then we're done. Wow. And then we're going to review. And then we're going to take the AP exam. And we're all going to do very well, right? And then
We're gonna party every day after the exam.
This isn't too much.
Sure, why not? But our party will involve also doing Fourier series. So after the exam, I do Fourier series, which is an extension of the idea of representing functions as polynomials. Okay, so let's get started. I want to consider a very interesting integral. What does this mean? Can I even write that? Well, I just wrote it, right. But what could I possibly mean by it? Does it make sense in terms of the integral as the limit of a Riemann sum? And the obvious answer is no, it doesn't make sense. Because the Riemann sum precedes by taking an interval a to b and partitioning that interval and then doing subpartitions and subpartitions so that in the limit, as the size of our partition goes to 0 of f of c times blah blah blah, then we say that that value, if it exists, is the value of our interval. Well, there is no way that you can take the interval from 0 to infinity and partition it. I mean, you can partition it, but you can't form a Riemann sum from it. The delta x's that you form, in particular, the delta x's that you form either would have to be an infinite number of delta x's, or they would have to, at least one of them would have to be of infinite length. So this integral doesn't make any sense. It is an improper integral. And in particular, we call it an improper integral of the first type. improper integrals of type 1 are integrals in this form: the integral from a to infinity of f of x dx, or the integral from negative infinity to b of f of x dx, or even the integral from negative infinity to infinity of f of x dx. And the key thing to understand is that we are not able to write this as the limit of a Riemann sum, which is what makes it improper. Well, you knew this was coming. If there are improper integrals of type 1, then there are probably improper integrals of type 2 and type 3 as well. So I want to consider, before we solve the problem here, or consider whether we want to solve it, we want to take a look at other integrals that are improper as well. Consider the integral from 0 to 1 of 1 over x dx. What do you notice about the function and the limits of integration? Yes, our function has an infinite discontinuity at x equals 0. Oops, I'm out of habit. There we go. That's my asymptote. And so what I'm looking at right here is an integral of a function in which I have a vertical asymptote at x equals a or at x equals b. I've written this informally like this. You recognize that this is really a limit statement, right? This is not actually saying that infinity is a number. Okay. So this is an improper integral of type 2. Now, why is it improper? Because you remember that the way in which we evaluated the limit of our Riemann sum was to compute the upper sum and the lower sum. And in the limit, if the upper sum and the lower sum approach each other, then that is the value of our limit. But here, the upper sum is always infinite. This is our big problem with the improper integrals of type 2, and that is that the upper sum is infinite. And so because of that, since the upper sum is infinite, it is never the case that the limit as the mesh size goes to 0 of the upper sum equals the limit as the mesh size goes to 0 of the lower sum, which is what we required for our Riemann sums to have a limit. That never happens. And the reason is really simple. When I draw myself a partition like this, this last rectangle right here always has infinite height. Excuse me. Okay. Well, sadly, there are improper integrals of the third type as well. But these are not so much a new thought as they are just a slippery thing to watch out for. Consider the integral from negative 1 to 1 of 1 over x dx. Anybody see the problem? Yes, there is a vertical asymptote smack in the middle in the interior of my interval of integration. This is an improper integral of type 3. And its problem is exactly the same as the improper integral of type 2, and that is that the upper sum is not finite. The only reason that we classify it slightly differently from the improper integral of type 2 is that what we're going to do is to take this guy and break it up into two types. Yeah, exactly. We're going to break it up into two. And so what defines an improper integral of type 3 is that we have the integral from a to b of f of x dx, and f of c is infinite for c somewhere in the interior of a to b. Okay? Everybody clear on our three types? The first type, we actually integrate out to infinity. Second type, we integrate from a to b, but we have a vertical asymptote. And the third type, we have a vertical asymptote again in the interior. Now what we'd like to do is to treat all three of these basically in the same manner. We're going to handle each one of these with a limit. So I'm going to consider, for today, I'm going to consider pretty much the improper integrals of type 1. And then tomorrow we'll handle 2 and 3. And just to remind you, we're looking at integrals of the form integral from a to infinity of f of x dx, or integral from negative infinity to b of f of x dx, or even this. So let's take a look at just this guy right here and consider what it might mean. I want to take a look at a function, maybe like this, that has the virtue that the limit as x goes to infinity of f of x is equal to 0. So that we have a horizontal asymptote y equals 0. This is our setup. And what I want to consider now is the area from A to some finite number B, like this. So that this area is a really simple Riemann sum that we can represent as the integral from A to B of f of x dx. Now, what do we want this symbol to mean? What we really want it to mean is the area of the unbounded region starting at A and going all the way out. What we'd like for this integral to compute for us is this area right here, if that makes any sense. Now, you might be thinking, it doesn't make any sense because our curve goes all the way out to infinity. However, I want to consider this possibility. So this guy should represent the area of the unbounded region. I want to consider this possibility. If I compute the area of the bounded region right here, and then I take the limit as b goes to infinity, then what would this mean? What would this look like? What this would mean is that I'm going to take this value b, and I'm going to move the goalpost out to infinity. And when I move that goalpost out to infinity, then what I am doing is essentially taking this region right here, and I am splitting it into two pieces. I'm splitting it into a tail that I haven't yet computed, and I'm splitting it into a head. And if, as I move the goalpost b out to infinity, then the head essentially becomes the entire region, and the tail might go to 0. So that if the tail goes to 0, effectively, I have found the value of this integral, which represents the area of that region. So we're going to take this as a definition. This integral means the limit of the limit of the Riemann sum. It is a limit of a limit. Now let's consider how this looks. We take this as a definition. Now, let's consider how this looks. For example, let's consider the integral from 1 to infinity of 1 over x squared dx. Here's our region from 1. This is an unbounded region. It goes out to infinity like so. And we would like to consider whether or not it has an area. So we're going to use our definition to rewrite this as the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx. For the evaluation of the improper interval, we always appeal to the definition first. You cannot do arithmetic with infinity. If at any point you find yourself plugging infinity in, you're doing it wrong. Don't do that. Physicists will do that. Sometimes they cheat. They're really doing limit statements. They're not telling you. Mathematicians, we're going to be careful. We will not do arithmetic with infinity. Okay. Now, this is a very straightforward limit. The integral of x to the minus 2 power is negative 1 times x to the minus 1 power. And this gives me the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. But now, as b goes to infinity, this is a very straightforward computation. This term goes to 0, so that what I get as a value is 1. And here is the meaning of this expression. What this means is that if I take the curve y equals 1 over x squared, and I start at 1, and I integrate out to b, then as b increases, the value of the area as a function of b is equal to 1 minus 1 over b. And as b increases, that area goes to 1. Does that make sense? So what we have here, right here, is an area function as a function of b. And then we're simply letting b go to infinity. Meanwhile, it should be fairly clear that the tail is going to be equal to 1 over b, right over here. That's the area of this unbounded region over here. And that tail has to go to 0 in order for the integral to have a value. Does that make sense as a procedure? Okay, cool. You try one. 30 seconds, go. Don't forget that your first step must be to appeal to the definition and rewrite like so. Yep. Justin, carry it home for us.
Oh, so it's the other and tangents
No,
Pi over 2.
it is pi over 2. Ooh. Go back to the graph of tangent. The graph of tangent has vertical asymptotes at pi over 2 and negative pi over 2, because the cosine of pi over 2 is 0 and the cosine of negative pi over 2 is 0. So therefore, when I invert the graph of arctangent, is when you have horizontal asymptote, y equals pi over 2, and horizontal asymptote, y equals negative pi over 2. And as x goes to positive infinity, inverse tangent of x is equal to pi over 2. Remember, that was one of our 3 points in our 3-point solution for the graph. Now, this is a fascinating result. Look at what it's saying. Here comes y equals 1 over 1 plus x squared, like so. And what we were saying is that the area of this unbounded region is exactly pi over 2. How about that? That means, theoretically, I could compute a value for pi by integrating, well, really, this entire region, right? Now, that's theoretically. In practice, to do it numerically, would mean taking ever larger values of b and continuing to add on, and that turns out to be a slow process. So you don't get to digits of pi very quickly by doing this. You can't. It just requires a lot of patience. It's not the most efficient way of building it. How are we doing? Does this make sense? Okay. Let's consider now a couple of integrals along these lines here. Interesting. Very similar to the last one, but a remarkably different result. We're going to handle it the same way by first rewriting as a limit. This is a non-optional step, just in case you were wondering. Must be done. And now, as we do, what is the antiderivative of 1 over x? Natural log of absolute value of x. And because all of my x's are positive on this region, I'm going to write that as just ln x. What's the natural log of 1?
0.
Yep. Now, slightly more challenging question. What's the limit as b goes to infinity of ln b?
Infinity.
Yes, it is.
Y'all shouldn't feel right.
What does it mean to say that this integral is infinite? What it means is that it doesn't have a value. The integral diverges. The integral diverges, which means that it fails to have a value. The opposite of diverges is converges. Exactly.
Oh,
So
I
our-
remember those from
yeah.
the last.
Our previous integral converges to pi over 2. And the notion of converging means basically it all comes together. That's literally what it means to converge. And in this case, what's all coming together are these little pieces of area that we're adding up all the way out to infinity. When you add up those little pieces of area out to infinity, my curve drops down quickly enough so that as I add them, I am adding on value that that is convergent. Whereas, in the case of the curve y equals 1 over x, this curve does not drop down quickly enough, and as a result, when I add up from 1 out to infinity, the area of this region is infinite, because the rate of change of that function is too large. is too small. It doesn't change quickly enough. It doesn't drop quickly enough. So this suggests to us that some integrals can converge and some integrals can diverge, and we wonder if there's a way to tell the difference. So this leads us to a couple of thoughts. But before we get to that thought, I want to look at one more divergent interval. It looks really innocent, doesn't it? And a naive student might take a look at this integral and think about what it represents, and might argue that this integral should be zero. It should cancel out, but it's not. Interesting. So why not?
Why not? So if you're negative close to
Right?
from B to 0, which is
Which is, but now we consider this limit. Oop, I changed my mind. We consider this limit, and this limit is very interesting because as we look at the function 1 minus cosine x, 1 minus cosine x is going to start at 0, and then it's going to go to positive values here. Let's see. 1 minus 1 minus cosine x. Yes. Starts at 0, goes up, hits a maximum when x is equal to pi. There we go. And then goes back down. There. Okay. Take a look at our function 1 minus cosine x and let e go to infinity. What's it doing? It's oscillating between -1 and 1. It does not converge to a value, but it also does not blow out to infinity. It simply fails to converge. And so we say this does not exist. The integral diverges. Notice the different terminology. The limit does not exist, so the integral diverges. Don't get those terms confused.
So we can never find area. I mean,
Well, it doesn't have an area. And the reason it doesn't have an area is that as you go out, what you're doing is, let's say you go out to this point right here. All that cancels, right? Good. But now as I add on rectangles, those rectangles are giving me different values of area that oscillate between +2 and 0. And so since I get an oscillating answer, I'm not converging to a single value. So those are the types of pathologies that you can have. You can converge, you can diverge out to infinity, or you can diverge by failing to come to a single value, usually by oscillating. Okay, so this raises an important question. Can I look at an integral and tell whether or not it's going to converge, even if I can't find its value?
yes.
Yes. Did you come up with our
Do you remember from last year? I actually saved a screenshot.
Oh, cool.
Like when we were.
I don't remember that you did that, but I'm glad you do. So, okay, so let's go there. Yes, about the P integrals. That's right.
So when you just said like we can tell like this for the 1/x, like the radius, it's like smaller. So we can all see this diverge or converge.
Good. Okay. Can we tell can we tell whether an integral converges? Well, the answer is maybe. And one way to do it is just compute it. If we can compute it, then hey, we can tell if it converges or diverges. But there are a lot of improper integrals that we can't actually compute very easily. And one of those, just to give you a for instance, would be the integral from 0 to infinity of 1 over 1 plus x cubed dx. Yuck. I don't know an antiderivative for 1 over 1 plus x cubed. I could actually come up with some effort using some techniques that we're going to learn, partial fractions, and we can do some complete square. It can happen, but it's ugly, right? I would like to be able to just pick this guy out of the lineup and say, hey, that integral is going to converge even if I don't know what line it is. So we're going to have a comparison theorem. We could even call it a comparison test. And that is this. If f of x is bounded by g of x and bounded by 0, and if the integral from a to infinity of g of x dx exists, is equal to L, then the integral from a to infinity of f of x dx also exists and is strictly less than or equal to L. In other words, if I can take an ugly function like 1 over 1 plus x cubed and compare it to a nice easy function, then I could immediately not only have existence, but I can also say that the value of that interval is less than or equal to L. I'm not going to do a proof of this theorem. It's not hard, but I just want the time for something else. But the spirit of the proof is like this. We have a function that is trapped between 0 and g, and if the integral of g exists out to infinity, well, it's basically squeeze theorem, essentially. Yeah.
But it won't equal 0?
It will be greater than or equal to 0. Right. But we knew that already. Yeah. Okay. So let's now come up with some easy comparison functions, and those are going to be our P functions. Yep. P integrals. Do we need to go back here?
Sorry.
Josh, you need me to go back?
No, I'm good.
Okay. The integrals of the first type. I want to consider these here because they're easy to integrate and they provide extremely convenient comparison functions. And we can handle them exactly as we have been, first by rewriting the improper integral as the limit of a proper integral, and at the same time rewriting our integrand as x to the negative p. Well, this is all very straightforward stuff. We integrate with the power rule as long as p is not what value?
1.
That means that we're going to need to have a special case for p equals 1 later on. But now the evaluation is very straightforward. I get negative b to the p minus 1 over negative p minus 1 minus 1 over 1 to the negative p minus 1 over negative p plus 1. Again, for p not equal to 1.
We can take out 1 over negative 2 plus 1.
Well, yeah, right. So this guy right here is pretty straightforward. 1 to the negative p plus 1 is just
We want
1, right? And negative, the opposite of negative p plus 1 is, of course, p minus 1. What about this term right here? Well, this term here is really very interesting. As b goes out to infinity, I've got a couple of options. If negative p plus 1 is less than 0, then that means that I am looking at 1 over b to the p minus 1, right? And then as b goes to infinity, this limit will go to 0. So that's one possibility. If negative p plus 1 is a negative number, then this entire term will go to 0. But if negative p plus 1 is less than 0, then that means that p is bigger than 1. On the other hand, if negative p plus 1 is a positive value, then that means that this whole exponent right here is positive, and as b goes to infinity, my integral is going to go to infinity. It will diverge. In other words, if p is less than 1. Well, what happens if p is exactly equal to 1? We already did this one.
Do not
We did this one right here. And when we did, we found out that the integral diverged. So that if p is equal to 1, then my integral diverges as well. So what we conclude then, taking all of our computations here and summing them up, we see that the integral from 1 to infinity of 1 over x to the p dx is equal to 1 over p minus 1 if p is greater than 1 and diverges otherwise. Does this make sense to everybody?
Yes.
Okay. Now, let's take this and apply it back to our yucky integral from this guy right here. Yep, I sure will. Okay. So, let's come back and revisit this yucky integral that we had previously. Well, I can reason as follows. The integrand, 1 over x cubed plus 1, is always less than or equal to what easy p function?
1 over x cubed.
That's exactly it. It's always less than or equal to 1 over x cubed. And because of that, therefore, I can say that the p integral right here is a no-brainer. It's 1 over p minus 1. Poof, done. Which means, therefore, that the integral from 1 to infinity of 1 over x cubed plus 1 dx converges and is less than or equal to 1/2. Isn't that nice? So we have a comparison test that is fueled by these p integrals as their ammunition. Does that make sense? last thing I need to talk about is what we do when we have integrals that go out to negative infinity. And this is a matter of definition also. By definition, we're going to do exactly what you think we're going to do, which is we're going to take now the lower bound and we're going to take that all the way back to negative infinity like that. Well, this raises an interesting question. How do I handle this guy? This requires special care because the tempting thing might be to simply rewrite it as the limit as b goes to infinity of integral negative b to positive. And you don't want to do that because that would impose a condition of symmetry on your integral. And you don't necessarily have symmetry. Go ahead.
Can we use something that appeals to infinity?
That's one way that you can do it, yes. So there are a couple of possible approaches. One way is to split it at any arbitrary point A. Like that, and then you have just two integrals of type 1 that you can deal with. A second approach is to do separate limits. Just to give you a for instance, the integral over the entire real line of 1 over 1 plus x squared dx. We know already this limit converges by comparison to the integral of 1 over x squared.
1. I mean, that's it.
Yeah, that's right. So and less than 1. Or in this case, degree. Well, can we do comparison? If we could split it at 1, we actually can't do comparison there because we're not integrating from 1 to infinity. So, interesting thought about that. So let me back that up. We can't use the comparison test with our p-series because our limits of integration are wrong. But if we do, write this like so, then what we have is now the double limit of arctan b minus arctan of a. And now if we take the limit on the inside, that limit goes to pi over 2. And if we take the limit on the outside, this limit goes to negative pi over 2. So that you get pi over 2 minus negative pi over 2, which is equal to pi. And that's it.
If we use the comparison, we don't have to use p, right?
If we use the comparison test very often, it is a p-series we would be comparing to. So those two work together.
But since we already did 0 to infinity with 1 over 1 plus
Well,
x, and equals pi
oh,
over 2.
yes,
So,
yeah, we can do that.